So today we are going to be talking about the gas behavior. Gases is one of the three states of matter that we have seen in this course. And the gas state is the most widely studied and the best understood of the three states of matter: liquid, solid, and gas. First, let's review what do we know about this gas state. And whatever wrong concepts may be in your head, we need to polish them and clean them up. If somebody walks in through that door and belongs to another planet and they have no idea what we mean by liquid water or versus gas water, and you are to enlighten this being, what do you say? How do you explain the difference between liquid and vapor water? What's in your head?
The compression of the particles.
The compression of the particles is what?
Where they are.
Okay, so you would begin to characterize what? The gas versus the liquid versus the solid. And you're saying that in which state the compression of the particle is maximized? In the gas state, the compression is maximized? I can't hear you. It looks different. We know what it is. We just need to dissect it. When I boil water, we've all boiled water. We've made tea maybe or coffee. And I have water in the liquid state. And I heat it, meaning I put an arrow with a triangle, meaning it's heat. And I get gas. Is this what I'm doing? Do I turn water into hydrogen and oxygen? Gas. Yes? No? Maybe? That is not balanced. We can balance it. Is that what's happening when I heat water? Is that a true statement? I'm hearing yes, I'm hearing no. I want to know why. Why yes, why no? We've done this. This is not new. This is a chemical change. This is a chemical change. Very good. So this is not true. That happens not if I have a triangle in there. If I maybe do electrolysis, then yes, I can break the bonds in water, and water is a covalent compound, and you have a bond between oxygen and hydrogen, and then you make new bonds. Okay, so that's a chemical change. When I'm heating up water, liquid, what do I form? Gas, H2O. So this is what's happening. And this is not a chemical change. This is a what? This is a physical change. So I start with A, water, and I end up with A, water. So what's the difference? How do I explain what's the difference if I'm starting with the same thing? Okay, so when I heat up water, I have a change of state. I do not change composition. I don't call that a chemical change. Do we see the difference between the two? So what's the difference between water liquid and water vapor if I'm starting with the same thing? This being honestly does not understand what do we mean by water vapor. So let's try to explain this. How do we do that? What happens when you're heating up water? The particles expand, meaning the molecules of water will separate. So we're talking of the same molecules, H2O, but in the liquid state, the neighbor's H2O is very close to the other H2O. Water is polar, and there are hydrogen bonds between the hydrogen of one water molecule and a neighbor water molecule. So the distance between two water molecules is just H2O number 1 and H2O number 2. The distance are going to be maximized. Okay? Because we're giving it heat, we're giving it thermal energy, And that thermal energy is going to be used to break those hydrogen bonds, these bonds here. So water molecule number 1 is going to be totally different. And I have a container, and I have the gas state. Water molecule number 1 and water molecule number 2 are going to be totally separated. They're going to occupy the entire container. So it's the intermolecular forces of attraction, forces between two neighbor water molecules, and the intermolecular distances that is changing. But the composition, H2O, is not changing. Okay, so we have used things like heat to describe this change, temperature. We have used the fact that it's compressible, the pressure in there. We have used the variable volume. So there's a few variables that we need to use to describe the gas behavior. Okay, so in the gas state, I still have the same composition, H2O, but the distance between water molecule number 1 and water molecule number 2 are as huge as they can be. So if I have the gas trapped in a 5-liter container, the volume of the gas is 5 liters. If I compress it down to 1 liter, the volume of the gas is 1 liter. Okay, so the molecules are very, very far apart from each other. So the variables that we need to use to understand the gas behavior are volume. We're talking about a gas trapped in a 5-liter container or a 2-liter container, and the volume is measured in milliliters or liters, right? That's not new to anybody, yeah? So the units of volume are not new. We talked about heating up this thing, so temperature was another variable that we need to use to describe the gas behavior. And in this chapter, we can only use absolute temperature, degrees Kelvin. How do we get to Kelvin? Celsius plus 273. So Celsius plus 273 gives me Kelvin, and that is a variable that I must understand so that I can study the gas behavior. 2 other variables are very important. The amount of gas that I have. The amount is going to be measured in moles. Okay? And if we have grams, how do we go to moles? We divide grams by the molar mass, like always, which is the number of grams in a mole of a substance, and that takes me to moles. And pressure was another variable that we addressed. Gases are compressible, and when we apply pressure to a gas, we can do that. So let's understand the units of pressure. In the city we live in Miami, no matter where you go, it seems like we're at sea level. Maybe if you go downtown, we're 836 Expressway, you get a little bit higher than sea level, but for the most part, pressure is pretty constant. 1 atmosphere. Okay, so the unit pressure is going to require a little bit of explanation. If I have a container, and this container has liquid mercury in here. Mercury is a metal. Remember mercury? In your chart, and the chart on the wall is blue, meaning it's liquid. And I take a glass tubing, a piece of glass tubing. Let's pretend that this is a glass tubing. And I invert it and I put it in the pool of mercury. The glass tubing, this is a meter stick, is maybe this big. Okay, so I have a pool of mercury and a glass tubing. The pressure that I have at sea level, okay, so I have defined sea level where Miami happens to be. The pressure that exerts on that pool of mercury is going to make the mercury climb up a certain height. Okay, so this pressure, if this pressure is sea level, 1 atmosphere, and I look at the height, how many millimeters, these are millimeters, I can see that my pool of mercury is going to climb from my right to my left index finger, 760 millimeters of mercury. Okay, so that is 760 millimeters of mercury. Millimeter of mercury is also called a torr. So in here, we have the units of pressure. We can talk about atmospheres, and 1 atmosphere equals 760 torrs or 760 millimeters of mercury. Okay, so in this chapter, we're going to look at pressure, temperature, volume, and amount. And we are going to, I believe next week, you have a gas experiment coming up. Okay, so we are going to, I'm going to try to get you enough information so that you can understand your experiments the following week. Okay, so far we've done that for acid and bases and redox and nomenclature and chemical reactions, so hopefully you'll continue to be that way. The way pressure can be measured, one way pressure can be measured is by the use of a manometer. So imagine a glass tubing, but now this glass tubing has the shape of a U. Manometer. Measure pressure. If I have a gas in side A and I have another gas in side B, if the pressure in gas A is equal to the pressure in gas B, the level in both sides would be identical. Yeah? That's easily understood. So there's mercury in here. If the pressure in gas B is greater, so now I'm going to shoot up pressure in B. And let's try to do the same thing. And now I have my gas in here, gas B, has a greater pressure. So is this column going to go down or up? If it has greater pressure, it's going to push it away and go down. Shouldn't have picked the manometer to begin with. I have no idea why it's doing that. Okay, so then gas B would go Anybody knows how to work tablet PCs here and enlighten me? Okay, so now I have A difference in pressure. The pressure of gas A would be what? Lower or higher? Pressure of A is lower than the pressure of B. And if I want to know what the pressure of A is, I need to measure this distance, which I'm going to call delta H. Okay, so the pressure of A is going to be different to the pressure of B due to delta H. So if I have the pressure of A and I know what this difference is, I get what? The pressure of my other gas. Okay, so I can measure pressures using manometer. And if this is open to the atmosphere, if pressure of A is 1 atmosphere, so I can call pressure of A 1 atmosphere, then I can find out that the pressure of B would be the change in height, delta H, plus 1 atmosphere, plus 760 torrs, or 760 millimeters of mercury. Okay, so if this is open, okay, so if BA is 1 atmosphere, or 760 torrs, then the pressure of B would be 760 torrs plus the change in the difference on the 2 column heights. Okay, so a manometer could be used to measure the pressure of gases. Okay, so this is full of mercury, this is full of mercury, and this is full of mercury. Don't touch it too much because it goes away. Alright, so from the 4 variables that we have, I am going to take 2 variables at a time, and this chapter is so easy and so intuitive that you are going to tell me how one variable affects the other one, And these are the different laws that we will be studying. We're going to be covering in this chapter. We're going to start with how does pressure and volume affect each other, keeping temperature and amount constant. Then we'll move how does volume and temperature affect each other, keeping pressure and amount constant, and so on. So we'll start 2 variables at a time until we get the big picture of how any one of these variables affect any other one. Okay, so that's going to be our method of approach. And in doing so, we are going to look at not everybody came out. First one is Boyle's law. Then we're going to look at Charles' law. We're going to look at Gay-Lussac's law. And these 3 laws are going to be really our first major one. Okay, so A would be the combined law, which is Boyle's, Charles, and Gay-Lussac together. Then we're going to look at ideal gas law. We're going to look at Dalton, and in an effort to understand the gas behavior, these 4 variables will begin to be examined. Okay, so Boyle's law is the first one. Okay. Boyle is talking about how does volume and pressure affect each other. Okay, so in order for us to understand this, I want you to imagine that you have a gas trapped in a container with a movable piston. So I have gas inside this container, and this volume of this container is, let's say, 10 liters. And the pressure that this gas has is 1 atmosphere, or 760 torrs, or 60 millimeters of mercury. And then I am going to affect my volume. And this is at constant temperature and at constant amount. I'm not changing the amount of the gas in there, and I'm not changing the temperature. Okay, so volume and pressure are going to be examined at constant temperature and amount. N stands for moles. So I am going to get my gas, and if this is 10 liters, I'm going to squish it down to 5 liters. Okay, so I move my piston down, and my original volume, I'm calling that V1, is 10 liters, and my second final volume, I'm calling it 5 liters because I went to half of it. So my volume, did it increase or did it decrease? It went down. My volume went down. So what do you think the pressure is going to do? Is the pressure going to go up, or is the pressure going to go down? The pressure is going up. Anybody thinks that the pressure is going down? So it's intuitively seen. If I have the exact same amount of molecules in here, and I have half the volume, these guys are going to be so much squished together. And they're going to be colliding among themselves and colliding with the walls of the container so much more than in the first initial stage. Now, if my volume decreased by a factor of what? It went from 10 to 5, so it decreased by a factor of 2. If you start at 10 and you end up at 5, you cut it in half, correct? 10 divided by 2 is 5, yes? So my volume went down by a factor of 2. My pressure, you're saying it's going to go up. So what is my final pressure, guys? 2 atmospheres. Very good. And how did you get that answer? Okay, so if your volume, this is what he said, if your volume is going down from 10 to 5, you're dividing by 2, 10 to get to 5. The volume is decreasing by a factor of 2, the pressure will increase by the same factor of 2. So if your original pressure is 1 atmosphere, your final pressure must be 2 atmospheres. Congratulations, you just defined Boyle's law. This is what Boyle did. Okay, so if you would have done this hundreds of years ago, it would have been your name, not Boyle, in there. How do we make a mathematical expression that says this? My original concentration, volumes and pressure were 10 liters in 1 atmosphere. My final ones were 5 liters and 2 atmospheres. What do you think? We now have to make a law, a general statement that says that volume and pressure are inversely related. They are inversely proportional. Meaning, if one goes up, the other one goes down. How do I say that mathematically? What do you think? 10 times 1 is what? And that equals what? 5 times 2 is what? 10. So if I multiply these two, if I multiply V1 times P1, I'm multiplying 10 liters by 1 atmosphere. I should get the same. That's if I did what? Multiply the 5 liters, what's V2, times what? P2. That is a mathematical equation known as Boyle's law that tells you that if my pressure goes down, my volume must go up. And if my pressure goes up, my volume goes down. So there, if one goes up, the other one goes down. So, okay, so if I have 10 times 1, I'm going to get the same thing as 5 times 2. 10 times 1 is 10, 5 times 2 is 10. Okay, so if I'm increasing my pressure, my volume is decreasing. So far, so good? Okay, let's pick 2 other variables. Now we're going to look at Charles' law. And Charles studied volume and temperature. Okay, so now I want you to imagine pressure is not changing at constant pressure and amount. See, I'm changing temperature and seeing how that is going to affect my volume. Let's say I have a gas trapped inside a balloon. Okay, so my temperature is 300 K. And temperature is 300 K. And I have 3 liters of a gas. Or just think of a balloon first. We're going to do it in a movable piston thing again. But if I think of a balloon, we've all had birthdays and blown up balloons. Just imagine a 3-liter balloon, not very big. And I stick it in the freezer. The freezer is still at sea level. I didn't move anywhere. So my pressure is not changing. I'm not adding gas or removing gas. What's going to happen to the volume of that? It's going to shrink. So it's going to get like a little tiny balloon. Okay? What about it after it shrunk? I take it back out. I don't do anything. I don't blow it up, or now my temperature goes back up to 300 and it went down to 100. What's going to happen? It's going to come back. Okay, so if I am cooling this thing from T1 300 to T2 100, if I am decreasing my temperature from 300 to 100 by a factor of 3, my volume is going to be what? My final volume is going to be 1 liter. Very good. So let's pretend that's a third of what I had originally. And that's going to be V2. And that's going to be 1 liter. Congratulations. You just described Charles' law. Now give me a mathematical expression that says that if temperature goes down, the volume goes down. Or that if temperature goes up, the volume what? goes up. Okay, so we stuck a balloon in the freezer and the balloon shrunk. What is it? V1? V1 times T1 over T1. Okay, they cannot be times, because when it's times, it means what? They're inversely proportional. And these are not inversely proportional, they're what? Volume and temperature are what? Directly proportional. If one goes up, the other one goes up. If one goes down, the other one goes down. Okay, at constant pressure and amount. So V1 over T1 equals what? V2 over T2. Temperature is very friendly. It's gonna agree with whatever the other variable does. Okay, temperature's going up, volume's going up, temperature's going down, the volume's going down. And it does the same with pressure. If I have Gay-Lussac under consideration, Gay-Lussac's law studies pressure and temperature at constant what? What are my other variables? Volume and amount. Okay, so I'm not changing my volume now. I'm having a gas trapped in a container and I cannot move this piston. It's fixed. And I cannot add more gas in there because that's not what I'm studying right now. I'm just looking at pressure and temperature relationships. Okay? And again, what happens if I have a gas, and this is whatever volume it is, it's not changing. This is not a movable piston. Okay, so this could be 5 liters, 10 liters, whatever you want. And at a pressure of 1 atmosphere. And at a temperature, and I'm going to write 1 because I'm going to have an initial set of conditions, and 2 because I'm going to have a final set of conditions. So my original temperature is 300 K. And then I heat this baby up. Triangle on the arrow means I put a little burner and I'm heating that baby up, and I cannot change my volume. My volume is not changing. It's constant. Okay, so my volume is still there. But my temperature is now going to go up to 900 K. I'm heating it up. What do you think the pressure is going to do? Okay, so I'm going to have the exact volume, same exact number of molecules in there. But my pressure must be what? 3 atmospheres. Okay, so you're getting me the answers, which is what your next test is going to ask. You're telling me that if I triple the temperature, my pressure is also going to increase by the exact same factor. And how do we say that? When they're directly proportional, pressure and temperature are directly related. How do we say that? P1 what? Over T1 is equal to what? P2 over T2. Okay, so that means that if temperature increases, that gas is going to get more and more thermal energy, and it's going to translate that into more kinetic energy, and it's going to move faster and faster, those particles of a gas, and they're going to collide among themselves much more vigorously, and they're going to collide with the walls of the container, and that's what's going to trigger an increment in pressure. So if the temperature is tripling, the pressure triples. If the temperature changes by 1.32, the pressure is going to change by 1.32, the exact same factor. And if one's going down, the other one's going down. If temperature drops, my pressure also drops. Yes? So far, so good? So now let's do our first law, which is the combined law. Combined law is really boils, Charles, Gay-Lussac all in one. How do you think that law is going to look at? What is it going to say? What was Boyle? V1, P1 equals what? V2, P2. That was Boyle, right? And then if my pressure is constant, if that guy is not there, when I changed my temperature, I had V1 over T1 or P1 over T1 equals what? V2 over T2 or P2 over T2. Okay, so if P1 equals P2, then I have V1 over T1 equals V2 T2. Okay, so this one right here, if P1 equals P2, I have V1 T1 equals V2 T2. If T2 and T1 are the same, then I have V1 P1 equals V2 P2. So I have all the laws in one. So I will get this guy out of here. No. Frame that. So at Boyle's, Charles, and combined law together. Okay. Let me give you another important one. Avogadro. So I'm just going to throw variables at you, and then we're going to throw numbers. Okay, let's just get the concept. Yes?
The temperature and pressure law doesn't apply to water.
It applies to any gas. Water vapor, any gas.
So usually when you freeze water, it expands.
Yeah, when you freeze water, liquid water. Okay, water is an amazing compound. Okay, so when water does that, those hydrogen bonds that I talked earlier need a lot of room. And if water didn't do that, we wouldn't be here to see it. Okay, so water is a totally wacko. It's a very anomalous behavior. And unlike most other substances, when it freezes, when you're talking about liquid water, we're talking about gas water. Okay? But yes, liquid water doesn't do what all the other liquids do. Any other comments or questions? Okay, I'm still in the second page of the module, trying to walk you through the different laws, and I'm at Avogadro's law. Good old Avogadro. We have seen the contribution of Avogadro. He defined a mole as 6.02 times 10 to the 23rd units, whatever they are, particles, molecules, atoms, dollars. We used it in all kinds of units. The same Avogadro studied the gas behavior. And he found out that if you have 1 mole of a gas, how many molecules would that be again? 6.02 times 10 to the 23rd molecules of this gas, whatever it may be. Water vapor, helium, neon. I'm just taking group 8, noble gases, helium, neon, argon, because they're gases. All the red people in the chart, in that chart on the left of the room, they're gases, right? So if you have 1 mole of helium, 6.02 times 10 to the 23rd atoms of helium, at standard temperature and pressure. And standard temperature and pressure in the gas law, standard temperature is 273 degrees Kelvin and 760 torr. Or what? What's 760 torr? 1 atm. When you have a pressure of 1 atmosphere, this atmosphere that we normally have in Miami, and 273 is what? 0 Celsius. Oh, thank God there's nothing standard about that. Okay, that's pretty cold. But if you had 1 mole of a gas, that many 6.02 times 10 to the 23rd particles of this gas, the volume of the gas will never change. and it will equal 22.4 liters. Okay, so at STP, if you change your pressure, if you change your temperature, this is no longer true. But at STP, so STP doesn't mean the oil treatment. It's standard temperature and pressure. Standard temperature and pressure. 1 mole of a gas occupies 22.4 liters. I am going to walk you through the first example on the bottom of page H2, which occupies a larger volume at STP. Example, exercise, which occupies a larger volume (2 grams of helium or 1 gram of hydrogen. And hydrogen is, how do I write hydrogen? H2. Which ones are the diatomics? Do we remember which ones are the diatomics? We look at the chart and the diatomics are N2, O2, F2. We put hydrogen on top, Cl2, Br2, yes? Well, these guys are gases. Br2 is a liquid. Okay, so we don't write H but H2. We don't write O but O2 because we are remembering module 1, I think that was. Yeah? Diatomic. It was an upside down T. Okay, so, and this is at STP. So I'm not changing pressure, I'm not changing temperature, but I have different amounts. So what do I need to do from here? Go to moles, and how do I go to moles? Moles of helium is going to be what? 2 grams of helium over the molar mass of helium, which is what? 1 mole of helium weighs, what does the chart tell me? 4 grams. So I look in the chart, helium has a molar mass of 4, so 2 divided by 4 is a half a mole. What about the moles of hydrogen? I have 1 gram of hydrogen. Over what? Not 1. Hydrogen happens to be diatomic. Did we hear the fact that hydrogen is diatomic? And this is where you goof when you're not paying attention. Okay, so if it's O, it's O2. If it's H, it's H2. Because these are gases. Okay, so it's the molar mass of hydrogen is what? 2 grams. Okay, so I have 2 hydrogens. It's 2 times 1 is 2 in a mole. So I have what? A half a mole of H2. So I have the same volume, the same pressure. I'm sorry, I gave you the answer. I have the same pressure, same temperature, same number of moles. So I must therefore have the same volume. Okay, so they're both the same. Okay, so equal number of moles at the same pressure and the same temperature will have equal number of volumes, same liters. Okay, so if 1 mole at STP occupies 1 mole 22.4, and I don't have a mole, I have a half a mole. Okay, so I have a half a mole of a gas. But I know that for every mole, I occupy 22.4 liters. So what's my volume, guys? Half of 22.4 is called the molar volume. So half of the molar volume. So these, both of these will occupy the exact same volume. Same volume for both. He and H2. Are we okay with this? Does this make sense? Okay, so we can make a relationship and use these equalities. 1 mole of a gas equals 22.4 liters only when we are at STP. Okay, so 22.4 liters is equal to a mole is going to be used just like you use 2.54 centimeters equals 1 inch. Okay, so far in this chapter I gave you 1 atmosphere equals what? 760 torr, or 1 atmosphere equals 760 millimeters of mercury. Those are equalities. We can jump from atmospheres to torrs, torrs to atmospheres. I just gave you another one. 1 mole of a gas at STP occupies 22.4 liters. It's like the size of a basketball. If I have, let's do another problem. Let's just review a little bit of what we said earlier, and you can tell me how to solve it actually in a couple of ways. Another problem. A sample of neon occupies 105 liters at 27 Celsius and 985 torrs. What volume would this gas occupy at STP? What volume would it occupy at STP? And what do I mean by STP again? Temperature is 273 Kelvin. And pressure is 760 torrs. I want it in torrs because my other pressure is in torrs. So how do you think we could solve through this problem? And you should be able to come up with 2 different methods. What would be the first method? Anybody? Combined law. What was combined law? V1, P1 over T1 equals what? V2, P2 over T2. Okay, so we need to define what's V1. We need to define what's P1, what's T1, what's V2, what's P2, and what's T2. So our strategy, if we're applying the combined law, is what's my V1? V1. 105 liters. Okay. What is P1? My original pressure. That's what? 985 torrs. What's T1? 27 plus, don't forget you need to add 273 to it. So that gives you Kelvin. It doesn't work in Celsius. Did you hear that? Yeah? And that's a common error. So put a watch out there. You need to add my next final volume is what I'm after. What's my pressure? Standard pressure 760 and my standard temperature is 273. So I can use that, plug in, and get an answer. Okay, let's go ahead and plug in. V1 is 105 liters. P1 is 985 torrs. T1 is 300K. V2, I don't know. P2 is 760 torrs. And T2 is 273 K. So I solve for V2. And it's 105 liters. 985 torrs is going to be on the top. 760 torrs is going to be on the bottom. 273 Kelvin is going to be on the top. 300 Kelvin is going to be on the bottom. So I just compute and I get an answer of 124 liters. How else could I have done this problem? I could have used what? Okay, let's just leave it there because I'm going to confuse you. You all understood this one, so let's just, yeah, the ideal gas law. Okay, so those of you who read, you can use ideal gas law to do this problem. So let's find out what the ideal gas law is. Okay, so on the top we said we were going to do different laws. Ideal gas law coming up. Yeah, we could have used ideal gas law and Avogadro's law and got the same. All right. Ideal gas law is going to be covered in lab next week. Okay, so your lab cannot be any sooner than Monday or Tuesday, so you're ready for it. An ideal gas law is one of these laws that you probably have had in high school, yes? How many people had this in high school? Some of you, okay. And what did it say? PV equals nRT. It has kind of a ring to it. PV equals nRT talks about an ideal gas, which is a gas whose for us, all our gases are going to be ideal, meaning the volume of the actual particles of the gas is tiny compared to the volume of the container, and the pressure that these gas exert against the walls of the container is the total pressure of the gas, as opposed to looking at the intermolecular forces of them. Okay, so P stands for pressure, V stands for volume, N stands for moles, R is a constant, and T is temperature in Kelvin only. Volume could be milliliters, liters, whatever you want. Pressure could be atmospheres, torrs, whatever you want. So I'm going to solve for R to see what the heck R is. R is going to be what? P V over N T. And let me just rephrase Avogadro's law. What did Avogadro's law say? It said that 1 mole of a gas at STP occupies 22.4 liters. Yes, we remember this? So let's plug that in there. At STP, what is my pressure? Pressure 760 torr. And my volume of this gas is 22.4 liters. And how many moles do I have? And what is the temperature? Standard temperature? 273. So if I use Avogadro's law, saying that 1 mole of a gas at 760 torrs and 273 Kelvin occupies 22.4 liters, which is a true statement, I could get the value of R. So if I plug that in there, what do I get? 62.4, and my units are liters in the numerator, torrs in the numerator, over degree Kelvin in the denominator, moles. R has all those units. Okay? PV equals nRT, where R is the universal ideal gas law constant. What if my pressure, I choose not to use 760 torrs, but if I choose to use 1 atmosphere, is that wrong? No, 1 atmosphere is 760 torrs. My volume is still 22.4 liters. I still have a mole of gas. And I still have standard temperature, 273 Kelvin. So if I compute this, am I going to get 62.4? I don't think so, because I changed one of the variables. So what do I mean by a constant? A constant is a number that doesn't change. But in here, when I compute this, I get 0.0821. Why it changed? My units. So my value's not going to be the same. If I want R in liter atmospheres over degree Kelvin mole, it's 0.0821. Okay? And it's still as constant as 62.4. I'm not giving you two values of R. I'm just changing torrs for atmospheres. Are we okay? How could we have done the previous problem using this statement. So in our previous problem, we had a sample of neon occupies 105 liters at 27 Celsius or 300 K. Because I added that to 273 to go to, and that's a good habit. The minute Celsius comes your way, right there and then, add 273 and change it to Kelvin so you don't forget. Because if you forget, you're lying. That is not directly related. And 785 torrs. With the volume, V, the temperature, T, and the pressure, I could find what?
R.
No, R, I already know. R is this. R will be given to you in a test, but you're going to do so many problems that you're not even going to need it. You're going to get it in your head. The faster you get R in your head, the faster your test will come. Next week in lab, you'll determine R. Or the week after, whenever you get to that lab experiment. So R we know. Do we know P? Yes. What's P? 985. Whoops. 985 torr. Do we know temperature? Yes. It's 300. Do we know volume? Volume? 105. Okay, so they're telling me that 105 liters of a gas at a pressure of 985 torrs on a temperature of 300 K, that's a fact, no? And I know R. So I have my volume, I have my pressure, and I have my temperature. What am I missing? I'm missing moles. So if I use PV equals nRT, I can solve for R, for N, and get moles. N would be PV over RT. So let's find out how many moles of a gas do we have. And then once we know the moles of a gas, we can bring it to STP, because Avogadro can do that for us. Okay, so what's the pressure? 985 torrs. What's the volume? 105 liters. What's R? What value of R do I choose? 62.4 in this case, because my pressure is in torrs. So I choose 62.4 if my pressure is in torr, degree Kelvin mole, and my temperature is what? 300 K. So when I multiply these, 985, what did you guys get? What's the number of moles that you get? 5.52, something or other? 48, blah, 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 blah. Moles. And then I do, okay, so they wanted to take it to STP. They want to know what is the volume. Now I have the moles. I know that at STP, 1 mole of a gas occupies 22.4 liters. I don't have a mole of a gas. I have what? 5.524 moles. Moles. So if 1 mole occupies 22.4 liters, I just multiply that times the molar volume times 22.4, and I should get the exact same answer. 124 liters. Okay, so this problem reviewed everything. Boyle's law, Gay-Lussac, Charles, which was all together in the combined law. V1, P1 over T1 is V2, P2 over T2. It reviewed Avogadro's law. 1 mole of a gas occupies 22.4 liters. And it reviewed the value of R, which was new. So far we're good. Let me just give you one more law, which is Dalton, which is the easiest of everything. So I leave that one for last. Dalton's law. This law is so easy that you are going to tell me what it says by answering the question in this example. Dalton addresses a mixture of gases. Okay, so far we've had just a gas. that occupies a specific volume at a specific temperature and a specific pressure. Now I'm going to have three gases. Gas A, and the pressure of gas A is 300 torrs. And I also have in there gas B, and gas B has a pressure of 250 torrs. Or I have more B's. Let's make it 350 torrs. And I also have in there gas C. I have a little bit of gas C in there. And the pressure of gas C is 50 torrs. So I have a mixture of three gases, A, B, and C. And I want to know what you think is the total pressure of this gas. P total. What's P total in a mixture of a gas? What is it? PA plus PB plus PC, so it's going to be what? 700 N torrs. 700 torrs. So what did I do? I added PA plus PB plus PC. Now make a this statement in words. What does Dalton law says? In a mixture of a gas, in a mixture of gases, the sum of the individual partial pressures equals what? That total pressure. Okay, so if I have a mixture of two gases, I have a container, and this container has water vapor in there, and it has oxygen. Okay, and I know that the total pressure, P total, is 760 torr, because I have this under normal atmospheric, and I know that the pressure of oxygen is 25 torrs. And I ask you, I'm sorry, the pressure of water. The pressure of water is 25 torrs. I ask you, what's the pressure of oxygen in there? What do I need to do? How did you get the 735? I subtract. Okay, so what I'm saying is the pressure of oxygen plus the pressure of water gives me the total pressure, and I just subtract the total pressure from that of water to get the other container. This is the easiest chapter ever, guys. Any questions? So we've seen Boyle's, Charles, Gay-Lussac combine Avogadro's ideal gas law and Dalton. We see 7 laws in one lecture. Have a wonderful day. See you next time.